Start, sir.
अभी शेयर मत करिए वो अभी शेयर नहीं किया ना ठीक
So start.
Sure, go ahead. Shall I speak?
Yes, sir. Start, please.
Okay. Good afternoon. Welcome to this fifth lecture in the MoES webinar series. I hope you have been enjoying the previous lectures, which have been very informative and very useful. Today, I'm going to talk about something which is, I think, basic to every one of us. I mean, every Indian thinks about monsoons. And the other thing which also he gets passionate, other subjects, of course, are something which you all are aware of, cricket and, of course, Bollywood. And monsoon is also something where all of us have our own views on it. So today what we are going to do is we are going to look at the very basics of monsoons, what the monsoon is, how is it formed, what causes the monsoon, and what are the reasons why it kind of varies from year to year. And finally, we'll take a brief look at this year's predictions, because there will be many other lectures which will be talking about all these, like, for example, how it varies from year to year, and also monsoon predictions. There will be much more lectures which will cover these subjects. So I'll just kind of give you what I would think as a bird's eye view of it. And so without further ado, let's start with my talk. And just a minute. Yeah. Okay, so I'll start about the basics of monsoons. And this is the outline. Sorry, it's a little bit busy, but what I would like to start with is about the mean monsoon, the cause of monsoons. And we'll look at the global picture. How kind of monsoon is it? Kind of a local phenomena, or is it a global phenomena? Then we go into how it kind of varies from within a season, and then we'll go to a year-to-year variability and the causes for it. Just briefly, we'll discuss about it, and finally, I'll touch upon the prediction for this year for 2020. So let's start with the most basic one, which I would like to call as the mean monsoon. That is, this is the picture from June to September. As you all are aware, the Indian monsoon or the southwest monsoon starts somewhere around 1st of June and ends somewhere at the end of September, or let's say early October. Of course, these days it kind of goes on till about 10th of October is what we have seen. So if we look at the mean picture, this is kind of a climatology, what we call as, that is average over a long-term periods. And then we see what are the features in it. So the reds are where you have the high rainfall. The blue is where you don't have any rainfall at all. And in between is the areas with less rainfall. So what I would like to point out right now is that you have this high area of high rainfall. That's just next to the west coast, which is next to the Western Ghats. You also see a high amount of rainfall on the west coast of Myanmar, which also has a lot of mountains. So this kind of a rain that we get is what we call as orographic rain. And also during the months of June to September, we get a lot of rain in the central part of India, which is what we call as a monsoon trough zone, and also along the Himalayan foothills. And what you would also would have noticed is that, there is very little rain in this area, that is Sri Lanka and parts of Tamil Nadu and parts of Karnataka, where the rain is pretty low. This we call as the rain shadow, or a very little rain, also called as a Bay of Bengal cold pool. And you also get a kind of a secondary maxima of rainfall in the oceanic region around 5 south. And actually, this kind of a comprehensive picture of what happens to the monsoon, both over ocean and land, we could get it only after we got the satellites. So satellites have been a boon in kind of understanding our monsoon in a very big way. And also, I would like to point out that one of the wettest regions of the country, or for the world, the Cherrapunji in Minaswam, they are at the same latitude as, let's say, Saudi Arabia. Now, isn't that interesting? So what's happening is that in Saudi Arabia, you just don't get any rainfall during this period, but one of the wettest places is Meghalaya, the regions within Meghalaya, just adjoining to Bangladesh. And that's because we have a lot of hills and mountains here, the part of the Himalayan orography, which kind of makes a very big difference to the amount of rainfall we get. So there are features which are kind of partly local in nature and partly which could perhaps be a part of a global system. So that's what we would like to see, whether it is a global system or it's a local system. And first, also let us look at whether it is a land-sea contrast. Like all of you would have heard in schools or somewhere that land-ocean contrast or land-sea contrast causes the monsoon. And here is a picture of correlation, which kind of tells you association between temperature over India and the rainfall over there. And what I would like to point out is that this correlation from June to September shows that if the temperatures over land are higher, then the monsoon is weaker, which is counterintuitive. But if you really look at it, if you're looking at rainfall in July, when the rain is much, much higher than in June, right now we are sweltering in May, and that is, but the land is much cooler. So obviously there is a problem with land surface contrast theory. And though it might kind of cause a trigger by heating the land and creating a low, but after that, it's the monsoon processes, the wet, moist processes, as we call it, that kind of takes over. These moist processes are basically where air kind of ascends, moisture comes out, it heats up the surrounding air and kind of builds up its own circulation. So this is, and as you can see, that it's negatively correlated, which means the association between monsoon rainfall and temperatures here is negatively correlated. That means it is not the land-sea contrast, which kind of drives the monsoon in a big way. It may have a role in triggering the monsoon, but afterwards it's the moist processes which kind of take over and run the monsoon itself. So is monsoon a global or a local system? That's something we need to look at. So let's look at that. And this is rainfall over the entire world, which is from a data set called as the TRMM. And you can see that if you look at the rain band, this is in the month of January. The top one is in January and the lower one is from July. Then you see that there's a continuous kind of a band which occurs right across the globe. This is what we call also as the ITCZ, and here also, and this is for July. And you will see that if you look at the Indian monsoon, this is the Indian region. It is part of the Asian monsoon system, which in turn is also closely linked to the entire globe. So what we are looking at, the Indian summer monsoon, is part of our the global system, which we call as ITCZ. We'll look at ITCZ in a moment. And if you look at the surface winds, you can see that in the month of January, all the winds are converging here. So this is what we call as the intertropical convergence zone, or ITCZ, and that's where the winds are kind of converging. And you can see that happens right across the globe. And if you go back and look at the rainfall patterns, that's also kind of coincides. This is in January when we are looking at it. This is where the wind is also converging here. And you can also see regions of high rainfall occurring there. And if we go to July, you see that there is a large change in the area where there is this convergence happening. Most of the convergence is happening in much to the north, especially in the Indian region. And also in the other parts of the world, you can see this convergence happening. So again, as we see now that monsoons are nothing but manifestation of the intertropical convergence zone, or ITCZ as we call it, in the Indian region. This is the typical position of the intertropical convergence zone in July and in January. The blue one shows the position in January, and in July is the red line. And you can see that the maximum excursion of the intertropical convergence zone occurs over the Indian region. In other regions, you can see hardly any movement. For example, over Americas, you can see that there is hardly any change, but the largest excursion of the ITCZ is over the Indian region. And well, rest of the world, it kind of goes close to the equator, but it comes as much as 20 or 25 north over the Indian region. So that's what makes the Indian summer monsoon unique. And there are many features which kind of cause it, which includes the presence of orography and also the land kind of being surrounded by three very warm and moist hot oceans, which kind of create a lot of source of moisture, which drives our monsoon and allows it to kind of happen at a much more northern latitude as compared to the other parts of the world. This is the rainfall pattern again. And as I said, that we are in this ITCZ, and the highest rainfall region in the month of July is in the Pacific and over the Indian region. And rain bands, as we can see, shifts with ITCZ. So what we are seeing as the Indian monsoon is part of the seasonal shift of the intertropical convergence zone. And when we talk of intertropical convergence zone, wherever there is high rainfall, usually it is kind of associated with very high vertical velocities. The blues that we are seeing here are vertical upward velocities, and the reds and the yellows, they are kind of the downward velocities. So you can see that wherever there is ITCZ, there is a lot of upward movement of the air, which causes the moist air to rise up. And as it rises up, the moisture holding capacity reduces because the temperature also reduces, and then the excess moisture that is there, it kind of comes out and heats the surrounding atmosphere and causes a pressure difference, which kind of drives this rain band or the rain systems. So in short, we can say that ITCZ is also a region where there is copious rainfall, and also a region where you have large upward velocity. This is the position in July, where you can see lots of blues here, which is where you have the upward motion related to what's happening over the Indian region. That is, our monsoon is also having lots of rain and also lots of upward velocity. And you would also notice that here in the mid latitudes, that is, let's say in 30 north or 30 south, there is always descending motion. And if we had seen the rainfall patterns, you see that there is hardly any rain in most of these regions. And that is the descending air kind of prevents the air from going up, and also prevents rainfall. And these are regions where we find most of the deserts over the entire world. If you look at the Rajasthan desert and let's say the Gobi desert and even the American deserts and Sahara, of course, all of them are in these latitudes, which are in the descending region of the ITCZ. That is, you have an ascending band zone where kind of air rises up, and then there is a descending region where there is the dry air goes down and then kind of prevents any rainfall from occurring. And that's how we have deserts in most of these mid-latitude regions. This is a section of that north-south circulation that I just mentioned. It's also called as the Hadley cell, which is named after the famous astronomer Hadley, and who kind of visualized that there should be a global circulation pattern happening, which kind of drives these intertropical, not at that time we didn't know it as intertropical zones, but as the trade winds and the convergence regions and the doldrums, as they used to call it in those days. And if you look at the schematic picture, that's where close to equator, which is where it is there in most of parts of the world, you have this upward motion happening, which kind of, and that's where you have a lot of cloudiness and rainfall occurring. And then when it goes up, it kind of moves towards the upper latitudes and then descends in these regions, which are the dry desert regions. And this is the region where you have a lot of rainfall, and this is the region where you have very little rainfall, and which is where we have the desert. And of course, there is also circulation happening in the mid latitudes and in the upper latitudes, which in the new system of things, the new theory is that these are actually eddies in the mid latitudes. Though there is, if you average it, it starts looking like another cell, which is called as the ferrule cell, and there is one more cell, which is called as a polar cell. But the new thinking is that these are eddies which kind of transport energy, and because the effect of rotation of the Earth becomes much more important in the mid latitudes as compared to the lower latitudes, that is the tropical regions or the deep tropics, there a direct cell is not possible, and hence what we have is basically eddies which transport energy and momentum to the higher latitudes. That's the new thinking. So what looks like a cell, if you average the picture, is not quite a cell. This is only the direct cell that we get. The rest of them are not quite direct cells. So now let's talk of onset of monsoons, which should be happening very soon. And what we are seeing here is the picture of the onset dates, the new normal onset dates, which have been recently announced by IMD. And if you look at it, the actual onset, what I'm talking of is the climatology, not for this particular year, but in general, in the climatological and the sense of a long-term mean sense, we have the first onset happening in the Andamans and Nicobars, and in association, you also get a onset in Thailand around 22nd of May. And then it kind of starts shifting northwards around 25th. You see this line, which kind of passes just south of the Indian region. And around 1st of June is the famous onset that occurs over mainland in India, which is the monsoon onset over Kerala. A little later, about a week later, around 7th, it kind of covers Karnataka. And then around 10th or 11th of June, it kind of reaches around Mumbai. And then it kind of keeps traversing for northward till about the early, after the first week of July or in the second week of July, it covers the entire country. This is 8th of July. So you can see that it starts, the first onset in Andaman starts around 22nd May. And the entire country, in a very climatological sense, it's not that every year this is going to happen. In some years, it may happen earlier. Some years, it may happen later. And there could also be jumps. It's not like there is going to be a kind of a smooth onset. It can change from year to year. And that kind of happens. But what we are looking at is the mean picture. And that it starts around 22nd May and covers the entire country by about 8th of July, or about, let's say, in the middle of July, the entire country is covered. And if you are looking at Delhi, the monsoon arrives around 27th of June. If we look at rainfall month-wise, if we look at in the month of May, there is very little rainfall over most of India. And parts of it is kind of just off in the Arabian Sea and maybe parts of Kerala, where you get some thunderstorms, and southern parts of peninsula, where you do get some thunderstorms. Thunderstorms, of course, occur over most of the country, but then there is not much rain. There are some few spells which occur, intense spells with thunder and lightning, but most of it occurs. If you are looking at it, the long-term average, it kind of is the rainfall, large rainfall areas is kind of primarily in Kerala. Now, if we move to June, when onset has occurred over at least large parts of the country, you can see that primary rain band is here in next to the western coast. That is the Western Ghat rainfall, which the orographic rainfall. The winds coming from the Arabian Sea, which are moist winds, they kind of hit this Western Ghats and try to rise up. And in the process, all the moisture kind of comes out and we get a lot of rain on the Western Ghats. And similar thing occurs in on the Myanmar coast. Now we look at the peak period of monsoon, that is July and August. This is more or less like what the picture we have seen of monsoon. That is, you have a large amount of rain here in this region, which is also a low pressure zone, which we call as a monsoon trough. And you all have rain along the Western Ghats and Northeast India and parts of Bangladesh and Myanmar mountains. Again, notice that there is hardly any rainfall happening in Tamil Nadu and the Sri Lankan regions. And August also has a picture which is very similar to that of July. And what we can notice is that there is a sharp transition. That is, when we look at in Arabian Sea, you hardly have any rainfall, let's say, till about 70 east. And then if you go further east, it is one of the most moist regions during this period. And to the west of it, there's hardly any rainfall. And that's partly related to the fact that the ocean here is not quite warm. The temperatures here are much higher, and here it is much, much lower. And that kind of prevents much rainfall from happening. And the winds are also very strong here, which kind of carry the winds to carry the moisture into the Indian region. Something similar thing happens also in August. Now we come to what we call as the withdrawal phase, that is in September and October. You can see that the monsoon, which was very strong in the previous 2 months, is now kind of moving, has become weaker in the month of September. And in October, you hardly see any rain except in the southern part of it. That is, in the southern part of peninsula, you do see some rain, but over the rest of the country, you see very little rain in October. But if you look at September, then you see that there is still some rain along the Western Ghats and also certain parts of the monsoon trough, that is this region, which we call it the monsoon trough, and also in the northern Bay of Bengal and adjoining eastern and northeast India. So this is the withdrawal phase. So what we have seen is the onset phase, the peak phase, and the withdrawal phase. And if you look at pressure, sea level pressure, as we said, there is a low forming here in this region. This is for July, this is for January. And we see that in January, the pressure over land is much higher as compared to that over sea, while the reverse happens in the month of July. That is, your surface pressure is much lower over parts of India. This part is called as, this low pressure part where you get a lot of rainfall is called as the monsoon trough, and the other part where there is a low pressure but there is very little rainfall occurring, that's called as the heat low. So the eastern end of the monsoon trough has very vigorous convection. By convection we mean a lot of clouding and rainfall, while the western part has very little rain, and we call as, even though there is a low there, we call it as a heat low, because it's only driven by heating at the surface and not by the dynamical processes. That is the advection of moisture and the rainfall, which kind of create this low to sustain here. That is not happening there. It is purely sustained by low temperatures, high temperatures over this region. That's why we call this as the heat low. So one end of the monsoon trough ends in the heat low, the other end kind of dips into the head bay, that is the northern Bay of Bengal. So this is also the pressure gradient in the at about 2 kilometers or 2.5 kilometers, 1.5 to 2 kilometers. And also you can notice that there is a reversal of pressure gradient between January, this is in January, where you have a high and then you have a low here in this period. So there's kind of a reversal of pressure gradient also occurs, which also drives the monsoon. And these are the low level winds at the same level. And in January, as we noticed, we saw that the intertropical convergence zone was much to the south, while in July, you can see this winds kind of curving into this to the Indian landmass. And this jet, where you have very high winds coming into it, is called as the westerly jet, or here we call it as the Somali jet, which kind of merges into the westerly jet. And it's kind of driven by the heating over the Indian region, the moist heating happening over the Indian region, and also is a major source of moisture into the Indian region. So it's kind of a feedback mechanism. This kind of supplies a lot of moisture, this westerly jet or the Somali jet, so to speak, which in turn kind of intensifies the circulation, heats up the atmosphere, and then that kind of drives the monsoon, the rain, which causes lots of rainfall, which in turn heats up the atmosphere, and then that kind of intensifies the jet. So there's a positive feedback mechanism happening between the circulation and rainfall. And because the winds are very high here, we also find that it kind of causes cooling over Arabian Sea, which is why here the temperatures are much lower. Generally, there is a kind of a threshold for clouding and rainfall to happen, which is around 27 to 27.5, which was discovered by the Indian scientists led by Professor Hadley, and also at the same time by Graham and Barnett in the American studies. So this kind of shows that there is a threshold. Below it, there is not much clouding and rainfall, but above that threshold, there is a large amount of rainfall. And we find that kind of a transition of 27.5 to approximately occurs in this region. And to the east of it, where the sea surface temperatures, SSTs as we call them, they are higher, they kind of sustain rainfall, while over here, where the temperatures are lower, it's not able to sustain it. And part of the cooling also comes from the high winds that happen over this region. If you look at the higher level winds, it's just opposite to what we saw in the lower level. The lower level, most of the winds in July happen to come from the west. So we call them as westerlies. And in the at higher levels, which is about 10 to 15 kilometers high, the wind is easterly. That is, it comes from the east. So there is a huge amount of shear, so to speak, that if you're looking at it in the vertical sense, you have westerly winds, that is winds coming from the west, that is from this direction in the lower level, and at the upper level there is a wind coming from the east. So which kind of creates a huge amount of change of velocity, wind velocity with respect to vertical, which we call as a big vertical shear. And also interesting to note is that there is this kind of anticyclone, which is a stationary feature in monsoon circulation. That is, we call this as the Tibetan anticyclone. And this is the tropical easterly jet, and this is the anticyclone, which kind of merges with the easterly jet here. And to the north of Himalayas, you see a westerly, the mid-latitude westerly jet. Here you have the easterly jet, and that is ubiquitous to the monsoon region here. That is the easterlies. That is a change in the winds is also a ubiquitous feature, as we have seen, both at the upper level and at the lower level. So now let's see, we kind of looked at the mean picture, but we know that every month, within the monsoon season, it's not that every day the rainfall occurs with the same intensity. There are periods when we get very heavy rainfall. Then there are periods when there is very little rainfall. So we know that, okay, there are spells where we call it as active, when the rainfall is very high, and periods when there is very little rainfall. That is, for example, this is for the year 2002, when there was very little rainfall for a long period in the month of July, which led to one of the biggest droughts in the recent history. While in 1975, the amount of rain was much, there were hardly any breaks, and the rainfall was much higher, and it was the seasonal cumulative rain was about 99 centimeters, while in 2002, which was one of the strongest droughts that we have seen, was 71 centimeters. The average long-term mean, according to IMD, is about 88 to 89 centimeters. So these spells where it is very intense, we call them as the active spells, and the times when it is kind of weaker and there's not much rain, then that kind of is called as a break spell. And if we look at the spatial structure of rainfall, during strong spells, this is where most of the rain happens. That is what we call as the monsoon convergence zone, or the MCZ, and some rainfall over, and of course quite a bit of rainfall over the western parts. But northeastern region gets very little rainfall at that time. These are like the composites. That is, we are looking at the departure from the means. So it is not the actual numbers, but the departure from the means. So it is higher than normal over this region during active spells, and also along the western Ghats and parts of Kashmir and others, and tends to be lower over Tamil Nadu and Andhra Pradesh and parts of Karnataka. While if we look at the break feature, there is very little rainfall over central part of India and most of other parts of western part of India, while the northeast and peninsula, so they get much more rainfall. So this feature is the kind of where in the active spell you get more rain over the northern parts and the central part of India, and northeast kind of goes opposite to the rest of the country as far as rainfall is concerned. So that's where this is the kind of a composite picture. It's not that every break spell or every active spell will give you a similar picture, but this is kind of an average over a long term that of what happens during an active spell and also what happens during a break spell. So if you look at what happens within a season in a latitude, in the north-south sense, what we see is that we have these northward moving rainfall bands which occur over the Indian region. This is something unique to both to Indian region, and to a certain extent it also happens over the Western Pacific. That is, you have kind of where it starts around 5 north or 5 south and then kind of moves northward. And then it kind of stays in this region, the trough zone. This is more or less the trough zone, that where it kind of hangs around for a few days. Then a second one generates here, and then it moves northward. So this has a typical periodicity. I won't call it a periodicity, but a time interval for about 30 to 40 days, And it is these kind of move from the warm equatorial region, which is the secondary region of high rain that we saw in the earlier picture. And then it kind of originates there and moves into the trough zone and happens with a typical period of about 25 to 30, sometimes even 40 days. Such a signal is also seen over West Pacific, that is 150 east. And why these kind of rain bands move northward, there are many theories for that. Some are based on fluid mechanics, some more on thermodynamics, and it's still a matter of research to say why these kind of rain bands move only in the Indian region. Some people think that it could be soil moisture related. Some people think it's because of the gradient of instability that also plays a role. So there are various theories, and it's still a matter of research that to see why exactly these rain bands move northward. And sometimes the revival from a break, that is, if you have an extended period of no rain, that kind of ends with one of these northward propagating rain bands. So we'll now again move to even shorter time scales. What we looked at was something which happens in the what we call as the intraseasonal scale, which is about 20 to 25 days. We move to even shorter time scales, which is like 3 to 5 days, when intense rainfall systems, low pressure systems, kind of form and move over the Indian region. And on the left that you see the picture, which is during the active phase, and on the right you see during the break phase. What you can see is that during the active phase, all the low pressure systems, these could be lows or depressions. We do not get cyclones because, as we saw, the shear is too strong to sustain deep convection and deep vorticity. So we don't get intense cyclonic systems during the monsoon period. They happen, as we saw just now, because with the Amphan, just before the onset of monsoon or after the monsoon, that is, let's say in the month of October to November, we get a large number of cyclones. But these depressions and lows, the depressions are a stronger form of the low pressure systems, which kind of form over the northern part of Bay of Bengal and move into the trough zone. So while the lows are weaker low pressure systems, but both of them give copious amounts of rain to the most of the central Indian and the northern Indian region. And what we find it interesting is that most of the lows and depressions, they form over a small region during the active phase. While if you're looking at the break phase, they form over quite other parts of it's kind of well spread out, so to speak. And there are far fewer number of lows and depressions forming during the break phase. And while they form much more vigorously during the active phase, that is, the active phase kind of gives you the large scale flows, which are kind of favorable for this kind of a cloud and convective activity to happen, while breaks are less favorable for this kind of a sustained convective activity, that is a sustained cloudiness and rainfall to happen. And these typically have a lifespan of about 3 to 5 days, and they move along the monsoon trough during the active phase. Now we have seen how it kind of, what is the mean picture of the monsoon. We have seen how it kind of varies within a season. That is, you have these northward propagating bands, which kind of start around 5 south and move northward with a period of about 20 days. And then we kind of saw the low pressure systems, which form over the northern part of the bay and move into the monsoon trough region. And we have also seen the circulation picture. But let's see how it kind of varies from year to year. And all of us are familiar that it varies from year to year. There are years when there is a copious amount of rain over the entire country, while in some other years, it could be that there is very little rain in most parts of the country. For example, here I have shown is the month of July of 2002 on the left, where large parts of northwest India, central India didn't get any rain. There was, of course, some rain in the northeastern part of India, and also, of course, during the along the western parts. And this is 2003 when the monsoon was near normal. And you can see that large parts of central India and northwestern India had much higher rainfall as compared to 2002. So this is what we call as intraannual variability. That is, there are years when if the rainfall is very, very low, less than 10% of the less than 90% of the long-term average, then we call it as a drought. Well, if it is more than 10% of the long-term average, which is around 88 centimeters, we call it as a excess monsoon period. Last year was one year when, after about 20 to 25 years, we got rainfall which was more than 10% of the long period average. So we know this we call as the intraannual variability, and this is a time series of rainfall which shows both active, drought and flood years. There were years when there was large amount of rain happening here. These are the blues that we see, and the reds that we see are also where there were very little, relatively less rainfall. So this is the -10. This is the long-term average, that is, which we are showing as 0, and these are the departures from the normal. So these ones which kind of cross the 10% level, we usually call them as droughts, and one which go above the 10%, we call them as excess monsoon years. Between them, it's more or less like being within the normal. So, and because that's the standard deviation of rainfall is close to about 10% of the Indian summer monsoon, about 10% of its long-term average. So these are years, and then you can see some of them are very strong years, some of them are much weaker years, and this is what we call as the intraannual variability. And we also see that there are some periods when there is El Nino, which is kind of warming in the eastern and the central Pacific region, and then there is a La Nina where it is relatively cooling over those areas. And there seems to be some sort of an association between La Nina, El Nino, strong monsoons and weak monsoons. So let's look at the cause of what causes these intraannual variations. Now we look at this is called as ENSO, which is the El Nino Southern Oscillation. ENSO, El Nino is the oceanic component, Southern Oscillation that happens in the Central Pacific. There will be a longer discussion of these issues in the subsequent talks, so I'll not go into the details of it. But what the Southern Oscillation means that there is much higher pressure in the positive phase. Generally, the surface pressure is higher over the eastern part of Pacific and lower over the central and western parts of Pacific, while the opposite happens during an warm event, which is the El Nino. So the Southern Oscillation is nothing but the atmospheric component, while there is a warming of the ocean on the eastern side during an El Nino, and a relative cooling on the western part. So these also seem to have an interaction with monsoon, a strong association. And if we kind of look at the correlation, that is the association between monsoon and El Nino, it comes to about 0.5 and minus 0.53. That means whenever you have El Nino, that is about SSTs are warmer over the eastern and Pacific regions, then it's likely to be the probability of getting high rainfall over the Indian region on a seasonal scale is much lower. And the occurrence of ENSO, we'll talk about Walker circulation in a moment, which is kind of an east-west circulation that happens. This modifies the Hadley cell that we saw in a few slides back, where we had ascending motion in the center of ITCZ and descending motion elsewhere. This disrupts this Hadley cell pattern. And so let's look at what this Walker circulation is. So if you look at the vertical velocities, we see Walker circulation that we are looking at, you see that there is again, the blues show upward velocities, and the yellows and the reds show the downward velocities. So here there is rising motion here on the western part of Pacific, and there is descending motion in this part of the eastern part and the central part of Pacific. This is a picture for January, and this is a picture for June. This is the kind of a climatological picture. Generally, there is ascending motion on the eastern side, on the western side, and descending motion on the eastern side. So you have a kind of a circulation where it rises here, moves eastward, descends, and then kind of comes back. So this is a pattern that happens. So this kind of a cell or a circulation that happens is called as the Walker circulation. It is named after Sir Gilbert Walker, who was Director General of the India Met Department, and who did a lot of studies on the cause of droughts over the Indian region. And he was one of the first to see that there is a kind of a linkage with what happens over Central and Eastern Pacific with the Indian summer monsoon. And in his honor, he did some path-breaking work on the Indian summer monsoon. In his honor, this circulation is called as the Walker circulation. So this is another picture of that. That is, if you look at it, since it's occurring over ocean, ocean also kind of couples with it. And there is a cooler ocean here, which kind of facilitates the descending motion here, warmer ocean here, which kind of gives you a lot of moisture, which kind of rises up. Then there is clouding here as it rises up. Then it moves towards east, comes down, and then this is what we get it. And if you look at in the ocean, what we call as the thermocline, that is much shallower. That is where you have a sharp temperature discontinuity, where below which you have cold water, and that is much shallower on the eastern side, that is on this side, while it is much deeper on the western side. So this allows much more, and the winds circulation is also such that there could be this cold water can come up very easily. So this is what we call as upwelling, which kind of keeps this part of ocean, even though it is on right at the equator. The temperatures here could be as cold as 23 or 23 to 24, sometimes even 22 degrees Celsius. So while it is much warmer here, this is one of the warmest oceans, which generally is above the 28-degree level, and thus it can kind of sustain convection, that is clouding and rainfall. And that kind of, so there's usually, in a climatological sense, there's much more clouding on the western side and much less clouding on the eastern side. So this is the Walker circulation that we have been talking about. And this is the normal general climatology that we are seeing. And these are the sea surface temperature patterns. You can see that the ocean is much more warmer on the western side. And this is in July and this is in January. So there is some difference, but you can see that generally the sea surface temperatures are much warmer on the western side, that's the Indonesian coast, and much cooler on the American side, which is the Eastern Pacific. And we can see that this also kind of coincides pretty well with the ascending motion here and the descending motion here, and high rainfall here and the low rainfall here. So how do SSTs affect rainfall and ascent? So there appears to be a relationship between rainfall and sea surface temperature, which I kind of discussed a few slides back, and it was discovered by some of our Indian scientists led by Professor Kargil. And of course, at the same time, almost at the same time, it was kind of also discovered by Graham and Barnett. And what we see is that this is kind of a threshold around 28. About 27.5 or 28, there's a large increase in rainfall, while it kind of increases much more smoothly or in a much less fashion till about 27.5 degrees Celsius. So this kind of a nonlinearity that we see kind of sustains convection above 27.5 or 28 degrees centigrade. And we see a rapid rainfall. So wherever regions generally where the sea surface temperatures are high, you get a lot more rainfall, while it is where it is cooler, then you hardly get any rainfall. So now we kind of ask ourselves, what causes this SST to have this structure? And this is the oceanic circulation that I just mentioned. So you have cold upwelling happening on the eastern side, and here again the thermocline is much deeper on the western side. That is this is the Indonesian side. So there is very little cold water coming from the bottom, while it's much easier, and also because of the winds, and you have much more upwelling, the coastal upwelling, which we call, and also equatorial upwelling, which kind of causes the cold water to come up. And this kind of prevents, as we saw from the sea surface, the relationship between rainfall and sea surface temperature. It's in the eastern part, it is in this region, while on the western part, it's in this region. So the rainfall is much higher on the western part, that is on the towards the Indonesian coast, while on the eastern part, that's the American coast, it's in this region. So you get much more rainfall on the western part and much less rainfall on the American side. So this kind of drives the Walker circulation. So, so you could say in some sense there's a piling up of water on the western side and a kind of a reduction in the eastern side. So this is circulation again, and with deeper thermocline, even if there's upwelling, there's not much cold water that can come up to the western side. So that's why it is in a nutshell, we have low pressure at the western end because of warm sea surface temperatures, while high pressures here, and that kind of drives our Walker circulation. And southern oscillation, its kind of measure is the southern oscillation index, which is defined in the following way. Positive values indicate strong Walker circulation. Negative values indicate weaker circulation. And we note that it is kind of quasi-periodic. There were periods when the SOI was fairly positive in most of the period, between 1920 to 1940s or 1950s. Then again, there were long periods in the 1980s when it was in the negative phase. That is, this was the La Nina or the negative SOI phase, and this was where we have more positive SOI, and those were the periods when rainfall was also much more copious over the Indian region. So there is a kind of association which we saw also earlier, a negative association between El Nino and Indian summer monsoon. So what happens during El Nino? For some reason which is not quite understood, there are many theories. One of the theories says that, okay, suddenly the easterly winds kind of get weaker. So what we call as westerly wind bursts occur, which kind of reduces the amount of evaporation happening in the central and the eastern parts of Pacific. Once the evaporation kind of reduces, then it kind of, the ocean warms up. And once the ocean warms up, because I mean, ocean is likely to warm up here because we are talking of being close to the equator. And if there's not sufficient evaporation, the sea surface temperature is likely to go higher. And once the sea surface temperature goes higher, then it kind of can sustain a lot of clouding, rainfall, and kind of modifies the circulation. The mean circulation was like this, with ascent here and descent here. But during an El Nino, most of the clouding happens in the central and the eastern parts of Pacific. And that kind of disrupts the east-west circulation, which in turn is kind of linked to the north-south circulation. And that this disruption of the east-west circulation disrupts our Hadley cell. This is the Walker circulation. This gets disrupted, which in turn kind of disrupts the Hadley circulation, which in turn kind of changes the monsoon, the pattern of monsoon rainfall during our summer monsoon period. So if you look at the SSTs, the sea surface temperatures during La Nina, then this is the top one is the climatological mean, and the middle one is where you have La Nina. That is, as you can see, the temperatures are much cooler here, and cooler than the average, which itself is fairly low in this region, 24 to 25 kind of a sea surface temperatures you get. And while in a El Nino, this kind of becomes warmer and you kind of can sustain rainfall. And this is the rainfall picture, very similar to what you get during, this is in the month of July. Then during El Nino, there is less rain over the Indian region and much more over the west, central and eastern Pacific. And also the rainfall over the Indonesian region also reduces. So that's the kind of disrupts the east-west circulation in El Nino because of warming in the central Pacific and the eastern Pacific. And if there is more warming in the central Pacific, research studies have shown that the Indian monsoon is more affected than when it is in the eastern Pacific. So this is the relationship which we also saw earlier. That is, there is a strong association between El Nino and Indian summer monsoon with a kind of a correlation of -0.53. So this is one of the major players which kind of show that, okay, this is strong. There is a strong correlation between the El Nino summer southern oscillation and the Indian summer monsoon. But that doesn't explain all the droughts that we get. There are droughts which kind of are associated where there is not much El Nino. One typical example of that was 1979, when there was hardly any El Nino or a very weak El Nino, but we had one of the strongest droughts in this. So we need to know whether that can only ENSO explains the entire Indian the intraannual variability. It doesn't appear to be so. So could there be any other player? So we look towards the Indian Ocean. There also appears to be a teleconnection between the Indian Ocean and Indian summer monsoon. Recently, it was some of the dipole mode about 15 to 20 years back was discovered, and Indian researchers played a very big role in finding this out. And it was, of course, the research was done in Japan, but quite a few Indian researchers were involved in it. And this is called as the Indian Ocean Dipole. That is, sometimes we find that the ocean is kind of warmer on the western side, and sometimes it is warmer on the eastern side. And not always associated with it, but when we also find that there could be more clouding on the western side, and there could be more in some other years, there could be more clouding on the eastern side. So this is called as a positive. If you're looking at the oceanic component, it is called as the positive dipole, and this is called as the negative dipole. And I wouldn't call it as an kind of a equivalent of that in the atmosphere is the equatorial Indian Ocean oscillation, because quite often equinox is independent of what's happening in the Indian Ocean. In the dipole, there's no one-to-one kind of a correspondence between dipole and equatorial Indian Ocean oscillation. But whenever it's in there is more convection on the western side, we notice that the monsoon tends to be a little stronger. While if it is on the eastern side, that is then in some sense you could call in a very rough sense as the negative dipole or negative equino phase, then the rainfall over the Indian region is much less. So there appears to be another player in addition to ENSO, that which also seems to have a role in kind of modulating the Indian summer monsoon. So if we combine the two of them, that is, if we combine equin, which is a kind of you could say indicates the equatorial Indian Ocean oscillation, and ENSO, we can kind of explain almost all the major droughts and the excess monsoon. So if you look at this region, this particular quadrant, this is where you have all the droughts, and here both the ENSO index is negative, which means it is not favorable, and equin index is also negative, which means it is not favorable for the monsoon. So bulk of the droughts that we see here are kind of in a region where both of them are not favorable for in the Indian summer monsoon. There were some very strong ENSO years, for example, 1997, when ENSO was unfavorable, but equino was more favorable, and that kind of led to a near normal monsoon. And in 1994, when ENSO was weaker, but equino was favorable, we had a near normal, excess monsoon. And the ENSO was in its dying phase, and then it kind of, the equino kind of took over. The exact mechanism which kind of links up these teleconnections with the Indian summer monsoon is a matter of hot research, not just in India, but all over the world. So now we have seen monsoons on a shorter time scale, the medium time scale, that is within a season, and then seen the active break spell and how it kind of varies from year to year. Now, I'm sure all of us are in the month of May, when it is sweltering hot, all of us are looking forward to the monsoon, and we also would like to know what would the monsoon be. So let's kind of take a bird's eye view again. I'm not going into the details of it, on how we kind of predict the monsoons. One way of doing it is the dynamical models, which are based on laws of fluid mechanics and thermodynamics, and are widely used these days for predicting weather and climate. Dynamical models have submodels of them, of the atmosphere, land, and ocean, which kind of interactively co-evolve, so that we kind of write these equations for the atmosphere, the ocean, which also have fluid mechanics and thermodynamics, and land, which essentially is more about thermodynamics, and they interact with each other. We know that if there is more rainfall over land, it's kind of going to cool the land and give a lot of moisture, which in turn can become a local source of moisture. So over oceans, we know that the winds, which are again driven by rainfall elsewhere, could kind of affect the state of the ocean. So all of them have to kind of evolve in a interactive fashion for us to get a long-term status of the monsoon, which is what we look at when we are talking of weather or long-term weather. That is when we are looking at seasonal predictions and also to climate. We use these what we call as dynamical coupled model. And if you're looking at long-term memory, that essentially comes from the ocean. And so obviously, preparing the initial conditions is very important. And this is done using a technique called data assimilation. At a later, somewhere in the later part of this webinar series, there will be a more detailed lecture on numerical weather prediction and data assimilation, where you'll get kind of you'll kind of know more about all these techniques. And in India, operational seasonal prediction using the coupled dynamical models has started in a big way in the last about 7 to 8 years, when the government decided to have a massive program. Obviously, monsoon is very important for us, and its prediction using the latest method is imperative. And under the Ministry of Earth Science, a new program was started, which is called as the Monsoon Mission Program, which was dedicated to improving the predictions of the monsoon at all scales, that is at short-term scales, 3 to 5 days, the extended range, that is about 40 days, about 20 to 40 days, and in the seasonal prediction, that is about 3 months or 2 to 3 months in advance. So models were developed for this, and they have now been given to India Meteorological Department, which uses these models to do these predictions on all these 3 scales. And if we look at the dynamical models, the monsoon prediction by Indian models has perhaps the best skill on all these scales. And of course, for a long time before computers became so big and we could solve these equations of fluid mechanics and thermodynamics, statistical models have been very much in vogue, especially for seasonal forecasts, and they do have a bit of a value, quite a bit of value, I would say, and we kind of use both of them to kind of get the monsoon prediction. So this is in the dynamical forecast framework that we talk of for the seasonal prediction. So what we have is an atmospheric model which runs at a horizontal resolution of about 37 kilometers. We have an ice model. At the upper latitudes, we have a lot of sea ice being formed. Then we also have a land model, which kind of looks at what happens to the sea surface, the land surface temperature and the moisture that is there, and the snow and whatever forms and all those. And we also kind of sometimes take the moisture that is falling and kind of form them into rivers and direct them to the ocean. All this is done through the land model. Some of these modifications, especially putting in the rivers and all, has been done in India, which is one of the few countries which kind of has a model which also has river runoff coming in a dynamic fashion. Then we have the ocean model, which right now in the monsoon mission model, we are using the MOM4, and it's global in nature and has a 0.5 degree resolution, which kind of translates in the upper latitudes to about 50 kilometers. In the tropics, the resolution is much finer and it's at about 25 kilometers, and there are 40 levels in the vertical. And this is the model part of it. Wow, the initial conditions, that is how you kind of drive your model, is equally important. And the ocean, the atmospheric initial conditions, they are given by our sister organization, the National Center for Medium Range Weather Forecast. They create those initial conditions using a method called GSI. And the ocean initial conditions are created by another of our sister institutes, INCOIS, Indian National Center for Ocean Information Systems, using a method called GODAS. In a later discussions in one of the webinars, we will hear more about all these. And these feed into the model, and then we crank it up on one of our supercomputers, and then we run it for at least about 9 months when we are doing a seasonal prediction. And then we look at the forecast that come out of it. And since we know that the initial conditions have uncertainties in them, we do a large number of perturbed initial conditions and create an ensemble of it and look at the ensemble to get the spread of it. So based on all that, and also on seasonal prediction, on the statistical technique, IMD kind of combines them And for the statistical model, these are some of the parameters that they use, which is from various parts of the world. And this is the period over which this is taken. And the combination of that is used for forecast. And this is the forecast which IMD has given for for this year's monsoon. And they have predicted it's likely to be around 100% of the long period average, which is around 88 centimeters. The forecast error is about 5%. And if you look at the probability of various occurring, you can see that above normal and near normal have a much higher probability as compared to a deficit. And of course, there is some chance of an excess monsoon, but if you look at the probabilistic forecast, it's likely to remain in the near normal range. If you combine these three, then you know that, okay, there is a high probability that we'll get a near normal monsoon. And these are from the dynamical models. This is the global picture of rainfall. Again, the blues indicate high rainfall regions. And if we kind of zoom onto India, this is from the February initial conditions from our climate forecast system developed under the monsoon mission. You can see all blues over most of India, which shows that it's likely to become a normal or a high rainfall year. And this is with the later initial conditions. We do it every month. And here also we see that when we come closer in April, we again see that the rainfall is likely to be near normal. And we have seen that El Nino plays a very big role. And these are the time series of SSTs in the Nino 3.4 region, that is in the Central Pacific. And we'll see that it's kind of below normal for most of the period in the monsoon period. This is from our model, the MMCFS. This is from the Europeans, who also kind of predict a similar condition to happen. And this is from the North American multi-model ensemble, which also predicts that the El Nino is unlikely to occur, that the probability of El Nino occurrence is likely to be low. And the other one which we talked of is the IOD, and that shows that it's likely to become a slightly negative IOD during the our monsoon period. So we'll have to look at how it kind of evolves. And other centers, including Bureau of Meteorology and ECMWF, also predict a negative IOD during our monsoon season. So in summary, I would like to say that we have seen, taken a bird's eye view of the monsoon. And we saw that it's not a local land, ocean, sea breeze kind of a thing, but it's part of the climate system. And it's nothing but the manifestation of ITCZ, or the Intertropical Convergence Zone, over the Indian region. We have seen that it has significant fluctuation within a season, that is, it has active and break spells. It also has northward propagations of cloud bands, which are unique to this region. Monsoon also, we have seen, has a year-to-year fluctuation. And the major players that could be determining what happens in the Indian our Indian summer monsoon could be both Pacific, that is the El Nino, and the Indian Ocean, which is the equino dipole. Both can have an influence on the Indian summer monsoon. And we also saw that under the monsoon mission program, a dynamical forecast system, which is comparable to the best in the world, has been developed and is being used for generating forecast. If you look at the monsoon of 2020 per se, there's a high probability that it will be near normal, and the probability of an El Nino occurring is low. Perhaps there could be some negative IOD being formed, and we will have to kind of look at it. And of course, I would like to add that in the last 10 to 15 years, a lot of research has been done, both under the Ministry of Earth Science and supported by Ministry of Earth Science and within Ministry of Earth Science in many Indian organizations. And that has kind of given us a lot of insight into the fluctuations of the monsoon on various scales. So it's kind of a very exciting field. And those who, especially the youngsters, who want to kind of look at a challenging problem, I would suggest that this is one of the most challenging and one of the toughest problems to crack. And they are welcome to take a crack at it. And at this point, I would like to stop and take any questions which might be there. Thank you.
Thank you, Professor Ravi, for a very informative and basic talk about monsoon. And there were overwhelming number of questions we received, and we selected 5 best possible questions that we can accommodate within this limited time. So it's in your chat window. So kindly type the question and answer. Thank you.
Okay, yeah, I can see the questions. The first one is about solar insulation and heating. So how does aerosol, that is primary and secondary, affect the ITCZ and hence affect the rainfall? And hence, can the lockdown affect this year's rainfall? As there has been a decrease in aerosol, a very good question is what I would like to say. And yes, there have been studies at my institute, that's the Indian Institute of Tropical Meteorology, and elsewhere on the effect of aerosols. And if it again depends on the kind of aerosol that we are looking at. If the major aerosol is black carbon, it can kind of heat up the atmosphere. And while it is heating up the atmosphere, it could kind of reduce the clouding. So, and if it is a sulfate aerosol, it can be it can kind of induce clouds, but at the same time, it could reduce the heating of the atmosphere. So it is a complex question where the jury is still out on it. And some of the reduction in rainfall in climate change scenarios, or the recent reduction has been attributed to aerosols. And it is possible that reduced aerosol could have an impact on our monsoons. So we'll have to wait and watch what happens to the monsoons in this reduced aerosol scenario. It's going to be a tough question to answer at this point, but yes, we know that aerosols affect both the secondary and primary and secondary effects. And secondary effects are still kind of a matter of research. But we know that, okay, it has an effect. Some of the sulfate aerosols could reduce rainfall if you're looking only at the primary effects. While the black carbon, if you're looking at the primary effects, can increase rainfall. These are based on research studies. But if you're looking at the secondary effects, they also are still a matter of research. So it's, I mean, giving a complete answer to that is difficult, but let's wait and watch. And this is going to be a very good experiment in some sense, fortunately for us, but unfortunately for the rest of the world, in the sense that COVID is certainly something we should not be happy about, but it has kind of given us a unique opportunity, a unique experiment where the aerosol levels are at their lowest in the last 15 to 20 years. So let's wait and see. And of course, there are many other features that I said come into play. For example, what happens over the Indian Ocean or what happens over the Pacific, these can also play a role. So let's wait and watch and see how it kind of affects us. It's certainly going to give us a new insight this year on the variability of the monsoon. So I'll take the second one. What are the effects of tropical cyclone on monsoon? What are the reasons behind the low or rare occurrence of tropical cyclones during monsoon? Another very interesting question. During the low occurrence, I guess is related to the fact that you have a very strong shear. At the lower level, you have these winds coming from the west, and at the upper level, you have winds coming from the east. That is the westerly jet and the easterly jet. So it's kind of sharing if any clouds or anything are formed, they're kind of just getting blown away by these very strong winds or the very strong shear, which kind of leads to very little occurrence. That's why we get a large number of lows and depressions, but we don't get any cyclones. I don't remember any cyclones in the last 150 years of data. Perhaps there could be one or two, which could be a rare occasion. And it could be the strong shear that we are seeing of the vertical wind. So the vertical shear of the horizontal wind. That is, you have the westerly wind here and the easterly wind here, which is kind of shearing it off, and that's like unlikely to form, which is not very good for formation of a tropical cyclone. But during pre-monsoon period, at this period that we have seen, we had Amphan, which would have churned up our Bay of Bengal quite a bit, and the SSTs are likely to get colder. So there could be a bit of a delay, which even IMD is also predicting that there could be a delay of about 5 days in the onset of the monsoon. Then the third question is there any delay of onset in recent years? The IMD has come up with the new onset dates based on the rainfall data. There has been some change. It could be related to climate change, possibly. And yes, there has been some change, but no drastic changes. Of course, the end of the season seems to have become longer than the change in the dates of onset. That is, onset may have changed by a day or two. In some places, it may have, there might have been a delay, but it's only in the matter of 1 or 2 days, which is a climatological value. And if you're looking at its standard deviation, that could be much larger than the 1 or 2 days of changes that we are talking of, because every year it is not necessary that the monsoon onset will happen on 1st of June in Kerala. Sometimes it could happen on 5th, sometimes it could happen on 6th. So if you're looking at the climatological dates, yes, there could have been some changes. But I would say that, okay, the mean monsoon picture has not changed, though at the end of the withdrawal, there has been much more significant change, that some of the withdrawal dates have increased by about 2 to 3 days in certain parts of the country. So the fourth question is there any relationship that exists between tides of Earth-Moon system and with that of the monsoon? Okay, that's an interesting question, but I don't think tides, they're always there. They're astronomical tides, and I have not seen any study, or I'm not aware of it, so to say, of any of the effect of tides of Earth-Moon system on the monsoon. And the fifth question is, can you explain why winds are more zonal at 200 hectopascal than at 850 hectopascal? A very, very good observation. Well, if you're looking at 850 hectopascal, what we are talking of is about 1.5 kilometers above the surface, typically 1.5 to 2 kilometers. And there, the frictional effects, what's happening at the lower level, the clouding effects, all these are likely to play a very major role. And we also need to, that's something I didn't go into, is the Coriolis effect, the effect of Earth's rotation. I just briefly mentioned it, but I didn't go into the depth of it. We have this Coriolis effect, which kind of gives you a geostrophic flow. So the flow, if it is purely geostrophic, is perpendicular to the direction of the pressure gradient. And the frictional effects reduce the geostrophic effect. And frictional effect tries to make the flow go from high pressure to low pressure, while the geostrophic effect makes it go perpendicular to the pressure gradient. And these, the frictional effects and also the effect of clouding, which kind of creates more convergence, is much more noticeable at the lower level than at the upper level, where the frictional effects are much smaller. And that kind of, so the flow is mostly geostrophic, and hence it is much more zonal at the 200 hectopascal level, where you're talking of about 10 to 15 kilometers in, at a level where the surface frictional effects are going to be less, and hence the flow is more zonal. Okay, I think these were the questions, and I think
yeah, thank you, Professor Ravi, for a wonderful talk and spending time for this, giving a lecture in this webinar, and we are very thankful to you. Thank you very much. I also thank the audience. So over to you, sir.
Thank you. Thanks a lot. And it was a wonderful occasion for me to do this webinar on the basics of monsoon. Thanks a lot, and bye.
Okay, we can go offline now.